Thanks, Abby. So good morning. I'm going to talk about mechanism design with set-theoretic beliefs. And this is joint work with my advisor, Sylvia McKelly. And by the way, we are both Sylvia and I are computer scientists, and I believe some of the audience here are also. So during the talk, I'm going to explain some terminology, some terminology that may be very well known to economists. Okay. Now, the goal of this work is to understand the power of set-theoretic uncertainty in mechanism design. And this is today's agenda. I'm going to talk about our motivation and then our model, which, by the way, as you will see later, is very agnostic. And then I'm going to define the revenue benchmark that we are trying to implement for single good auctions. And then I'm going to show you actually it is impossible to achieve this benchmark under classical solution concepts. And then, therefore, we need our solution concept, which, by the way, as we will see later, is very conservative. I'm going to tell you what does that mean. And finally, it comes our mechanism. Okay? So, motivation. What is mechanism design? From our point of view, mechanism design does the following. It is optimization without information. Now, where is the information? It is with the players. So the players have types, have preferences about different outcomes. And the mechanism designer has to try to leverage such information and the player's rationality in order to achieve some outcome satisfying his own desired property. Okay. Now, by the way, in our case, desired property will be revenue in auctions. Now, what is a player's information? A player may have information about his own payoff type, right, theta I. And he may also have some information about the other player's types, theta minus I. Here, this minus I means the set of players except I. Now, the first part is what we call the internal information. This part the players know for sure, 100%. And we do not consider, in this work, we do not consider a player's uncertainty about his own types. Now, the other part is the player's external information. Well, this part, it may be complete or incomplete. I'm going to explain the terms next slide. But the first question is, which type of information do we want to leverage? And our answer is both. So we want to leverage all possible information in the system to get some better property. But which type of information do you think is easier to leverage? Well, it turns out that when the setting is of complete information, that is, the players' types are of common knowledge among each other. Means everybody knows that our types is like this. Then the case is pretty easy. As you can see, the designer looks pretty happy there. And basically, the conclusion in this setting is almost everything that you are interested in can be done here. A lot of work in this literature. However, when the setting is of incomplete information, the case becomes much more complicated. What has changed here? Well, for each player, now he knows his own true type theta I, and he knows some other extra information denoted by these dot dot dots. What is this external information? The designer has no idea, but he wants to leverage this information. So maybe the first question he needs to ask is, how are you going to model this type of external information? What is this dot dot dots? Now let me give you some classical alternatives. By the way, these alternatives fall into two different extremes. The first extreme, we model the player's external information by not modeling it. That's why I put this empty set there. Means that we just assume the players do not have external information. Well, how about if they happen to have? Well, then we just ignore them and work that. Of course, this is one extreme. And the other extreme is that we assume the players have very well formulated distributions about the types of the players. This is this distribution D. Now, what does this mean? This means for each possible type profile, the player have a precise probability associated with it. So what is the probability of this type? It is maybe 0.1345. what is the probability of the other one might be 0.278, something like that, very precise. Now, for the first extreme, we have a bunch of dominant strategy mechanisms which allow us to ignore the external information. Well, on the other extreme, we have a bunch of Bayesian mechanisms which deal with probabilistic distributions. However, I must say the following, that from our point of view, the first extreme is mighty pessimistic, while the other extreme is mighty optimistic. Why? Because if you think about real life, it is very possible that players may have extra information about each other. So a company hires somebody from the other company, and the company can certainly learn something from this guy. It's hard to imagine the company knows nothing about each other. Well, on the other extreme, it is hard also to imagine that the players have a very precise distribution associated. Maybe I cannot tell what is the probability the type of the other guy is like that. So even without doing anything, just by looking at this big gap, look at this big space there, our reaction is, well, there ought to be something in between. There ought to be a middle ground. And for example, you can imagine in auctions, a player's information may look like the following. See, I value the good for $50, and I believe that one of my competitors values it for at least for more than $100. So do I know who is this guy? I don't. Do I know what is the exact value? I don't. Do I know what is the probability that his valuation is 101, 102, etc., etc.? Well, I don't. Right. This is the only thing I know. And this type of information, as you can see, does not fall into either extreme and is currently not leverageable. And this is what we are trying to modeling. So, now how does our model look like? As I promised you, we are going to model the player's set-theoretic beliefs about the true type profile theta. So theta is a particular component in the whole type space, capital theta 1 times capital theta etc. times capital theta n. Capital theta I is a type space for player I. So in auctions, in single good auctions, capital theta I is just the set 0, 1, 2, 3, up to some big number v, for example. So we only deal with finite cases. Therefore, we assume there is an upper bound for the player's valuations. Can be 1 billion, 1 trillion, some large number, but as long as it's finite. Now, the player I is informed about the theta I, and he has some other information about theta minus I. And we are going to denote his own belief about this theta by bi. And this bi is nothing but a set of candidates. But it has to satisfy the following consistency requirement. That is, for each type profile in bi, the ith component has to be his own true type theta I. This reflects the fact that this player has always sure about his own true type, right? But besides that, we absolutely put no requirement about this bi. It can be anything. Actually, you can think about this bi as kind of a laundry list. It's just a set. There's no structure associated with it. There's no partial order, no distribution, or whatever. It's just a list. But something can be said about this set. The first is that it is totally consistent with the players having a Bayesian, right? And what if, say, the player's belief is that, what is the probability the types of the others is theta minus I prime? It is, well, 0.135, etc., etc. Now, where is the set-theoretic belief? Well, you just ignore everything with 0 probability and look at the support, put them together, and this will be your set-theoretic belief.
You want to forget the probability. So maybe some of them are obtained with high probability and some of them are obtained with
right,
very tiny
right.
probability, and for you it's the same.
Yes, for us, we are only going to look at whether it is 0 or positive.
So you are not leveraging information that
We are not leveraging this probability distribution because we do not know whether this distribution exists or not. Yeah.
But in particular, if the agent were a Bayesian and put probability, at least some probability on every possible
Mm-hmm.
then you have nothing to leverage.
In that case, yeah, in that case, you can see that the players in the set-theoretic belief, he believes that everything is possible, right? And then the set-theoretic belief will be everything.
So it's incomparable.
It is compatible.
It's incomparable.
It is incomparable. Yeah, yeah,
You're
yeah.
also
Yeah.
losing information you might have.
Yeah, if you have a strong confidence that the players have the distributions, maybe you should use marathon for the single good auctions.
But there's an intermediate.
Mm-hmm.
There's an intermediate position, which is
Mm-hmm.
perhaps you can't treat an agent as having a single probability distribution.
Mm-hmm.
But there's work which has allowed for an agent to have some range of probability.
Incomplete distribution, exactly.
So
Something like.
that possibility seems to be left out here.
Yeah, that possibility is not a part of the model. So basically, so you're saying that, for example, I think this guy's probability is between 0.2 and 0.5, but I don't know exactly what it is. This type of thing is not part of a Bayesian, is not a part of the set-theoretic belief. I mean, the players can, of course, in that case, you can still write down the set, right, which is everything with non-negative. But that is an extra structure. You may have or you may not have. It is incomparable here. Yeah. I think there are some literature studying that type of incomplete distributions, but it's not part of here.
There's a large literature
Yeah.
on decision theory
Mm-hmm.
where agents have multiple probabilities.
But I think in game theory now, somebody also, I think there are some literature there.
Also in game theory.
Mm-hmm.
Could you create another hybrid between these where you think of distributions on the set-theoretic beliefs then?
You can. Then you need to model the player's beliefs about the beliefs. That my belief about your belief about this set
You have
is
all
this
sorts of
this
issues
type of
about
thing.
Whether they sample consistently across them or something, right?
This is a kind of a high-level structure of the player's belief, and we are not going to model that today. Actually, I'll get to that a little bit now. So actually, as I said, we do not take any assumption about whether the distribution exists or not. So this is an assumptionless thing. That is, the players can always be able to write down such a set, whether he has extra information or not. And as we just said, if the players is such that he thinks everything is possible, then you just write the set to be theta I times everything. And if the setting is happen to be the complete information, then this set is just a singleton. And you can write anything in between. In particular, you can express the thing that player I may think player J and player K always have correlated types, things like that. But the other thing I want to say is why we use the word belief instead of knowledge is that we want to reflect the fact that beliefs may be wrong. So we all seen this thing happen in real life that somebody may hold wrong beliefs about the world, but this guy may still react according to his own belief without realizing his belief is actually wrong. And we allow this case to be expressed here. So we just say that a belief is correct if the true type is actually part of this thing. Otherwise, it is wrong, but then it's totally allowed. Now, this is regarding to your question about what if the players have beliefs about each other, right? And this is not a model today. I put unnecessary there because the thing is, no matter how the beliefs about the beliefs are going to look like, they are not going to hurt our mechanism. Therefore, we are okay with not modeling them. Now, with this said, again, I want to emphasize this point that no matter what the belief structure might be, the players, you can always write down a set about the type candidates. So this is not an assumption, this is the reality. And why we say the model is agnostic, because we want to leverage this reality whether or not the players have underlying Bayesian, and whether or not he has extra structure. For example, the partial distribution, this is an additional structure on top of this. Or whether or not some player may have some partial ordering about the set. It's totally fine. So we are taking the worst case. And of course, at this point, I hope the model is clear. And maybe the most crucial thing we want to ask is, can we work in this model? Or more precisely, what is the social choice correspondence we can implement here? Now, this is a little bit for computer scientists. So a social choice correspondence is a mapping. For each type of profile in the type space, it maps to a set of outcomes. And the interpretation is that if the true type profile were this T, then this set is the desired outcome which the designer wants to get at the end. So designer doesn't know which.
T is the vector of all types. In this
T?
picture,
T is a vector,
of
yeah.
all types.
So when I say a profile, this means a vector indexed by the players. So designer doesn't know which one is the truth. He can only say that, okay, if this is the truth, then I want this much. If that is the truth, I want that much. This is a social choice correspondence. Now, before defining any specific social choice correspondence, actually, let me point to you that by modeling explicitly this external information, we are actually giving the designer a richer language to express what he can do, what he wants to do. And okay, by the way, I'm putting the Bayesian part outside the picture because we are not taking this probability distribution in this talk. So we are talking about the other side. Now, as you can think about, if we do not model external information, then the social choice correspondence can only take input about the true type profiles. Well, on the other side, of course, because we can always write down this set of candidates, we can always put this thing as an extra input to the social choice correspondence, meaning that the designer wants to leverage this type of information. And as you can easily verify, whatever we can write down here can always be simulated by something there. So this is really a richer structure. And maybe some of you still remember, Silvio has given a talk about this thing here long time ago. And in that work, we actually work on robustness in this type of models. There we talk about privacy, collusion, etc., etc. But today, what we want is just greedy. We want revenue in auctions, period. So there is no privacy, no collusion today. Okay? Now, this is what we are going to achieve, the second belief revenue in single good auctions. Remember this picture? Now, this is how it becomes. The second belief is what I'm going to define, our revenue benchmark. Now, what is second V here? It is just the second highest valuation in the auction, which, as you may know, is the revenue that the second price mechanism can guarantee. So if the valuation are ordered in this way, it's just set 2. What's the relation? As I'm going to show, our benchmark is always greater than or equal to a second valuation. So by trying to achieve our benchmark, we will always get something, and there's nothing to lose. So let me define this second belief benchmark by example. Assume we have 3 players, and the valuation looks like that. Now, what is player 1's belief? He believes that the true type profile can be nothing but one of these 3. Notice 1, the first component is always his own true type. This is consistency. And notice 2, this belief is not correct, right? So the truth is not there. But the players can have such beliefs, and let's see what type of information we want to elicit here. So we're going to do the following. For the first profile, take the max in these numbers, which is 95 there. The interpretation is the following. So if the first profile were the truth, then player 1 knows that there is always some player, namely player 2, he has valuation at least this much. Now we do the same thing for the other profiles. And what is the number we get there? We get a 95 and a 99. Now we're going to take the mean of this set. And this is going to be the number we want to elicit from this guy's belief. By the way, it is 95, as you can verify. Right? We call it G1 because this is player 1, the guaranteed value from player 1's point of view. Guaranteed means that, according to his belief, no matter what the true type profile might be, it is one of these candidates. And then there will always be some player who values the good at least this much. But whether it is player 2 or player 3, he doesn't know. And again, this guaranteed is really despite of anything else, despite of Bayesian, despite of any extra information, or despite of any partial order.
So can you say again in what sense it is guaranteed?
In
what sense 95 is guaranteed?
That is according to player 1's own belief. He believes that the true type profile is one of these three. Therefore, there has to be some player values at least this much. And it doesn't matter whether he has probabilities associated there. Now, another thing I want you to notice is that this guaranteed value is at least the player 1's own true type. Right? You take the max and the mean is still there. Now, how about player 2? This guy is very confident. So he believes that the true type profile can be nothing but this singleton. Of course, he's wrong. But so what? We can still elicit some information from this belief. Indeed, we do the same thing. We take the max, we take the mean, and what you get is this 80 there. Now, third player. This guy has no external information. He believes that player 1 and player 2's valuations can be anything between 0 and the upper bound. And for this setting, we can do the same thing, and you can verify that the guaranteed value from this guy's point of view is exactly his own valuation. And by the way, this belief of player 3 is correct, right? And as you can see, this is general. If somebody's belief is correct, then the guaranteed value will never be more than the maximum valuation, because the true type is always there. You take the max, and the mean is always less than this much. Now, this is a revenue goal we want to achieve. The second belief is just defined to be the second highest among the set of guaranteed values. By the way, here it is 80, which happen to be the highest valuation. But of course, this is not the case. It might be higher, might be lower. But the following is also general, that if everybody's belief is correct, then the second belief has to be no greater than the highest valuation. As you can think, if a player's belief is correct, then his guaranteed value is no greater than this much. Then, of course, you take the second highest, it is still no greater. Right? Now, at this point, actually, it is pretty easy to compare this one with the second valuation. You see, it is still written there, right? The guaranteed value is greater than or equal to the true valuation. Therefore, the second highest is greater than the second highest. Again, what does this mean? This means that if we try to achieve the second belief instead of second valuation, then we can always get something, possibly very high, and we are not going to lose anything. So, why not? Now, you may also ask, what if the players do not have external information, right? What if everybody just look like player 3? Then the thing is, it can also verify the benchmark will naturally decrease to second valuation. And again, it's confirmed that we do not have anything to lose. So, of course, now the question becomes, can we implement this benchmark? Now, during the remaining part of the talk, let me tell you, the answer is no under classical solution concept. And the answer is yes under ours. Okay? All right, so now we have this model, the set-theoretic model clear, and we have the second belief revenue defined. Now, let me give you some bad news first. It is impossible to implement the second belief revenue under classical solution concepts. Well, this is not their fault. This just happened to be the wrong tool to handle set-theoretic beliefs. Just like you cannot hope to cut a steak with a spoon.
Will you end up being able to implement the second belief with, do you need more than one round of interaction to do this?
We will need that, actually. Okay. You are right.
You have. It seems like with one round you can't implement this.
You are talking about the mechanism or the solution concept. Actually, they are different. So the mechanism is normal form, but solution concept, you need one round of elimination. I'll get to there later. You have the right intuition. Now, what type of classical solution concepts we are considering? We have examined a bunch of them, and I'm going to go through them one at a time. But of course, here we only consider solution concept in the incomplete information setting. What does that mean? That means some solution concept, for example, Nash equilibrium, or for example, subgame perfect equilibrium. They are wonderful solution concepts, but they are not verifiable in this setting, and thus they are not part of today's talk.
So what do you mean by verifiable?
Because if a player, if he doesn't know the complete type profile of every player, then given him a strategy profile, he cannot even tell whether this strategy profile is a Nash equilibrium or not. He can only tell whether his own strategy is the best response to the others, but he has no way to figure out whether the others is not.
So you're just saying that the solution concept doesn't apply if there's incomplete information.
Yeah, this doesn't apply. So I'm saying that
That I agree with. Unverifiable seems.
I'm just saying, okay. So I'm just saying that I'm not going to consider this solution concept here. Now, the first solution concept we are going to examine is dominant strategy. This is a very strong solution concept. As you may know, so a strategy Si of player I dominates the other strategy Si prime if no matter what the other players are going to do, the utility of using Si is greater than or equal to the other one. And in some cases, inequality is strict. So a strategy is dominant just means that it dominates all the other strategies.
Now it has to dominate only all the others according to the belief?
No, there is no belief in the picture. This is really for all S minus I, means that no matter what the other players are doing. Yeah. So you may know that this technically is called a weakly dominant. This is the solution concept we are going to examine first. And later, I'm going to also tell you something about the others. So what happened here? As you can see, I put this dominant strategy in this extreme. Why? Because it doesn't allow us to look at the external information. And our theorem just tells that there's no mechanism which can generate this benchmark at dominant strategies. So another solution concept we are going to examine is, we actually examine is,
There's a stronger theorem which says that having dominant strategies, the best you can do is the second valuation.
Actually, that one has no external information in the picture. Right? If you think about because if you put external information in a picture, you cannot use a revelation principle, just say that it can be simulated by a mechanism which has the player simply report the true valuation, right? Because the external information part is missing here.
That's true, but the theorem applies whatever the information is.
I think the theorem is proved basically by using revelation principle. And if you use that, then because revelation principle has no external information in the picture, I'm not sure that one applies, actually. Yeah. Actually, I can give you an example. Maybe we can talk about this offline. There is a dominant mechanism, in the sense of very weakly dominant, that actually gets this benchmark. But actually, there is something wrong there. We can talk about this later if you want. Now, another one we examine is undominated strategies. Now, I'm not going to define exactly what it means for a mechanism to implement the benchmark at undominated strategies, but the bottom line is that our theorem tells it is impossible to get it. And the third solution concept we examine is ex post equilibrium. So again, I'm not going to define exactly what it means, but it belongs to this word. So more precisely, this is a little bit different. So for the first two, the theorem says that it is impossible to get there, even you want to approximate this benchmark up to some constant factor, and even when all beliefs are correct. Now, if you may remember, this all beliefs are correct means that for all players, this theta belongs to this BI. This is crucial to be there, because if we allow the player's beliefs to be wrong, then basically it becomes totally trivial to realize that it's just impossible to get this benchmark under these solution concepts. So actually we are proving something even a little bit stronger, that even when the beliefs are correct, you can still not get there. Now the third one is a little bit different. So some mechanism may be able to do something there.
I have a question about
Mm-hmm.
There's no way to elicit this information
Yeah,
by any mechanism that works with, let's say, undominated strategies.
exactly.
I'm just wondering what happens with a very simple mechanism which just asks every player to say
Mm-hmm.
who values,
Mm.
in his belief,
Mhm.
who values the good
To
more,
report the
more.
valuation and the belief.
Yeah, we just
And,
we all just publish their belief. And for
Yeah.
$1, you promise them $1 in order to
Uh,
value their belief.
He doesn't know who values more. I mean, you saw in the example, sometimes
doesn't.
the second, sometimes the third, sometimes the fourth.
Yeah, but it's correct. So,
So
the
actually-
correct pattern appears in the intersection of all of them, right? The correct pattern appears, and then
actually, yeah.
the owner of the good will know this.
Yeah, actually, that is a very good example.
The first price, not the second price. I mean, I don't see why.
The thing is, that one is not a dominant strategy, and so yeah, you can try to report everything, and you can give the players $1 by reporting, and then if this $1 is constant, doesn't depend on what he reports, then he doesn't have incentive to do that, right? But if this $1 will depends on how much he reports, then that will not be dominant. So he will always have some incentive to overbid. Because you see, the truth is there, but he doesn't know which one is the truth. He may try to overbid a little bit to get more reward. So telling the truth cannot be dominant.
It's not clear to me why if it's $1 is fixed, it doesn't work. But doesn't matter.
We can talk about it later.
Too many equilibria, I think that's the problem. One equilibrium would be everyone tells the truth, but then everything else is also an equilibrium too. Or a lot of other things are also equilibria because you don't have a strong enough incentive to tell the truth.
Yeah, that is part of the reason. Okay, so for the third one, the thing is some mechanism may be able to get there, but our theorem tells that no matter how the mechanism is going to work, the mechanism is going to be inherently fragile, even you want to approximate, even when all the beliefs are correct. Now,
I don't know if you want to, so you're going to get into ex post equilibrium later? Because
if we have time.
at least according to the way that I would use the term, in this setting which is a private value setting, that is my valuation doesn't depend on your information.
Yeah.
There's no difference between ex post equilibrium and dominant strategy equilibrium.
I think you are right, actually. So in some sense, but I think what exactly you can say is that there is no difference between ex post equilibrium and very weakly dominant strategies. That is, you remember this dominant there we require is that the inequality is strict at some point. But this ex post equilibrium, if you want to find a counterpart, that will be very weakly dominant, means that the inequality always holds at some point. That I agree, that very weakly dominant strategy is not different from ex post equilibrium. And that one is actually also inherently fragile for the same reason. So next, what we are going to focus a little bit, let me give you some more details about the dominant strategy part. Why? Because this perhaps is the most simplest impossibility result I can show you without defining this terminology there. So how does the theorem look like?
Well, I have a question.
Yeah.
So, I mean, just to understand these impossibility theorems compared to what you're going to give us later. So you're always going to be able to give us the second belief. I mean, you'll be able to recover that value even if people's beliefs are not correct.
That's true.
So what happens if there are just, like two of us and I believe yours is, you value the thing infinitely and you believe I value it infinitely?
First of all, there is an upper bound, but this upper bound doesn't really matter. The thing, yeah, exactly, we are going to get there. The mechanism is going to give you.
But neither of us value it that much, though.
Yeah, the thing is, if the player's belief is wrong, the mechanism is not obliged to give the player non-negative utilities. Think about it in the real life. I mean, some player may have wrong beliefs and behave very badly, but if he wants to do that, we have nothing to help.
But are you going to
No,
or are you
not.
trying to recover that much utility for the bidders?
We're going to return that much money to the designer.
But why would I ever want to participate in an auction if I think I'm going to get a negative return?
Because if you believe, when you're holding a belief, you always think the belief is correct, right? And when you think the belief is correct, from your point of view, your utility will always be positive. That's the participation.
So you're saying I don't think that the outcome that ends up occurring is even possible.
You think it is possible that from your point of view, you have this belief, and you're going to reason about your strategies according to your own belief. And from your point of view, your utility is going to be positive. And of course, you may not realize what is the truth underlying there. Maybe as we are going to add.
What you said is right, that the real outcome will shock you because you didn't expect.
Yeah, you might be shocked.
So in effect, I attach zero probability to the real outcome.
You will not be shocked here, right? Because she talks about correct belief. So the outcome.
No, we're not talking
So
about
in the
this.
impossibility theorem, we're talking about the correct.
That was the question.
Yeah, in my mechanism, we allow the belief to be wrong.
Maybe we can
So,
postpone the discussion till we
yeah,
get
okay.
to that mechanism.
All right. So basically what we are saying that if for any constant epsilon, there's no reasonable deterministic mechanism implement this benchmark when the beliefs are correct. So a little bit of term, what is a reasonable mechanism? We want to say that A, the mechanism is finite, so each player only have finite many strategies. And B, a mechanism allows the player to opt out. So meaning the following, that for each player, he has a particular strategy, that if he uses that strategy, then no matter what the other players are going to do, his utility is guaranteed to be zero. This reflects the fact that a mechanism cannot just do nothing and simply ask the player to pay him 10 million, right? This is not a mechanism. We want the mechanism to allow the player to quit the game. So you may also want to use the other notion that we simply require the player's utility to be non-negative at dominant strategies as captured by individual rationality. That will also work here. If you want to use that one, you will essentially get the same result. It's just our choice that we want to give the player some explicit choice to quit the game. Now, second theorem is about the probabilistic mechanisms. And basically, the same thing can be said, except that the approximation factor now becomes, for any epsilon greater than a half, you cannot get this much. Now, originally, I want to give you the proof about this theorem. Why? Because I want to give you some idea about why this classical solution concept do not work, so that you can stop thinking about it and forget them, and then we can move on. At this point, I'm not sure we can still do that. So let's give a little bit. Anyway, the proof is really simple. We only need 2 players, and everything fits in one slide. Should we skip? Okay. All right. So this will be why the dominant strategy mechanism fails. So these are the 3 numbers. We have little h, capital H prime, and capital H. And this satisfies this relation. So this is a goal the mechanism want to achieve. Right? Let me put it there to remind you. So what we are going to do, we are going to play 2 mental games. Very simple ones. The first one, I want to imagine the following case. Player 1 has a very high valuation, and player 2 has a very low valuation. Player 1 has no external information at all. He believes that the player 2's valuation can be anything. And now player 2 has a lot of information. He believes that the player 1's valuation is at least capital H, but can be anything else, can be anything higher. Both are correct, exactly. This is what I wanted to verify. This game, the beliefs are correct. Now, this benchmark is exactly capital H. Why? You can check by definition. If you still remember what is the guaranteed value of player 1, well, you take the max and then you take the mean. It is capital H, etc. You get capital H there. And then for player 2, the guaranteed value is, again, you take the max everywhere and you take the mean. It will be capital H. Of course, the second highest is still capital H. Right? And this is a little bit notation. This DMT means dominant. this is the dominant strategy profile in this game. Of course, by hypothesis, this revenue is at least this epsilon of the benchmark. Now, what we want to show is that, unfortunately, the revenue can have to be strictly less than this. Of course, this is a contradiction. Now, how are we going to do that? We are going to play the second mental game. So I want you to think about this situation. Player 1 still have a higher valuation, but not that high, just capital H prime. Now, player 2 have the same small valuation, little h. Player 1 still have no external information, and player 2 still has a lot. He believes that player 1's valuation is at least capital H prime, and it can be anything higher. Again, the belief here is correct, and the benchmark now becomes capital H prime for the same reason as before. Now, this is the same notation. This is a dominant strategy profile in this game, and the revenue has to be at least this much, which is greater than little h, by the way. Now, I have the following claim, that for each player I, utility of player I in this second game as this dominant strategy is non-negative. This is not hard to see, right? Because the mechanism is reasonable, it allows the player to opt out. Therefore, either the dominant strategy is the opt-out strategy or it will dominate it. Therefore, utility can only go up. So QED. Now, let's remember this claim by putting it there. That is, for this dominant strategy, a player always have non-negative utility and the revenue is that much. This is another little bit notation. This A prime, P prime is the outcome of this dominant strategy. So A prime is either 0 or 1 or 2, meaning who gets the good. 0 means the good is unsold. Now, P is the price profile. PI is how much player I pays. Now, I claim the following, that in this outcome, the good has to go to player 1, and his price is at least this much and no more than capital H prime, and the player 2 pays nothing. Why this is the case? Well, this is exactly this second line here, right? Because the player have non-negative utility, if you give the good to player 2, you cannot charge him more than little h. And the revenue you get is no more than little h, which is, of course, too small. And then you give the good to player 1, you cannot charge him his true valuation, which is capital H prime. Let's see. Now, remember this inequality, this will be the key later. Now, okay, let's come back to game 1 and prove what we want to show there. Think about player 1. I claim the following, that in the first game, if player 2 want to use his strategy DMT2 prime there, then using the dominant strategy for player 1 always give player 1 better, at least the same utility. And why this is true? Well, we have seen this before already, that if these two dominant strategies are the same, then the utility are the same. Otherwise, the first one will dominate the second one in game 1, and the utility can only go up. Now, of course, the utility of the other strategy profile is at least h minus capital H prime. Why? Because a mechanism is such that you give it a strategy profile, it will give you an outcome. It doesn't matter whether we are in game 1 or game 2. So this is the same thing. Now, for player 2, I claim that these dominant strategies are just the same. Why? Because the valuations are the same, the utility functions are the same, and dominant strategy are the same. And again, this is that dominance is defined over valuations, not about beliefs. So player 2 has different beliefs in these two games, but this doesn't affect his dominant strategy. And this will be the key also. Now, putting these two lines together, what do we have? We have that for this dominant strategy profile, player 1's utility is at least this much, and player 2 is at least that much. Why? Player 2 has non-negative utility because he can opt out. Right? I claim this is enough that for us to derive this contradiction. Because again, if you give the good to player 2, then you cannot charge him more than little h. But then you give the good to player 1, to give him the lower bound of this utility, you cannot charge him more than capital H prime. And that's it. This is all we need to show. Now you look at this slide. There are a lot of mathematics, a lot of formulas there. But the essence is very simple. So, give you a little bit of summarization. What do we have here? We have two games. One has very high valuation and very high information. The other has a very low valuation and very low information. However, player 1 in the first game can always pretend he has low valuation. Of course, player 2 has beliefs to tell which one is the case. But the mechanism using dominant strategy does not even try to look at this guy's external information. Therefore, the mechanism has no way to distinguish whether we are in the first case or the second case. And it cannot deliver more revenue in game 1 than in game 2. And this will be the essence. And all the impossibility theorems I stated here and some things that I do not state here all have the same flavor, because nothing really works here. Now, bottom line is that there's no classical way to implement the second belief revenue. Now, question, is this good or bad? Now, let me tell you that from my point of view, I think this is excellent. Why? Because now we have more work to do. That we need to really think about some new idea, to come up with some new notions, to really get this benchmark what we need. Yeah.
By the way, just to go back to something we were talking about before.
Yeah.
When you say no classical way, you're ruling out any kind of Bayesian mechanism, even Bayesian
That's true.
mechanisms where people have multiple probability distributions.
That's true, because we say that it should work whether or not you have this, right? So, all right, so at this point, I think we are clear with the models, the benchmark, and why classical solution concepts do not work. Now, I want you to forget this classical solution concepts, and let's move on to our notion, strictly conservative implementation. And actually, I want to show you that from our point of view, this is not just another arbitrary solution concept that happened to work. We really think this is the right way to leverage the set-theoretic beliefs. And let me show you in 3 steps how we are going to derive the idea there. So the first step is a very classical solution concept, very simple. Just 2-step iterated elimination of strictly dominant strategies. Of course, this is not a new solution concept at all, right? So this is how it works. Think about Alice and Bob playing a game. Each one of them has a bunch of strategies, A, B, C, X, Y, Z, etc. Now, I just want to forget the names of the strategies, just denoted by each dot strategy there. Okay. So Bob trying to decide what he wants to do. And he does so by first looking at what Alice is going to do. So for example, Bob figure out, look, the second row in Alice's strategy set, each one of them is strictly dominated by something else. Now, Alice is rational. She's not going to use this type of stupid strategies. So let's eliminate them. Now, given that Alice is only going to choose strategies from that side, Bob will realize that, okay, his second column strategies, each one of them is strictly dominated by something else. So Bob is going to eliminate them as well. And that's it. At this point, Bob will stop and choose some strategy from this set. And this is a 2-step iterated elimination. Now, a pretty classical one. How about we try to apply this solution concept and generate the benchmark?
Alice will do the same.
Alice will do the same, but in the other way. Yeah. But the thing is, there is something hidden in this solution concept. Why we cannot use it? Because for Bob to realize what Alice wants to eliminate, Bob has to know exactly what is the valuation of Alice. However, in our model, what he only have a set of candidates, right? This is an incomplete information setting. So Alice is not even able to figure out Bob is not even able to figure out what Alice is going to eliminate. And he's not able to figure out what he himself should eliminate. So the surviving strategies, despite computational complexity, the players simply do not have enough information to finish the computation.
But it's possible, given what I believe about you set-theoretically,
Exactly.
that I can rule out
Exactly.
some strategies as being dominated, no matter what your
Exactly. That is a very good point, and this is the next trial, exactly. So that you are saying that we want to leverage this set-theoretic belief, so we have to bring this set-theoretic belief into the picture, right? We cannot just without looking at it. And, okay, I have just tell you this, that if Bob believes that Alice is of type A, he should eliminate that. Then Alice of type B, he should do a different elimination. And he knows nothing about that, so he has some difficulty about figuring out what to do. Now, the second trial, which is a much better proposal, we want to bring into picture the set-theoretic beliefs because we want to use that. And exactly as what Eric just said, let's go through the player's type profiles in his belief set. Now what? Now assume the first one, for example, is t minus I were the truth. Then, of course, the player now is in a good shape. He knows precisely what the other players are going to eliminate. And then he can carry on this second step computation. For example, he figures out this strategy D is dominated by another strategy A. And he will do the same thing for each type profile candidate in his belief set. And for example, he figured out that this strategy D is dominated in each one of these cases. And then we want the player to get the conclusion that we don't want to use this D. We want to eliminate it. Okay? But as I have another question here, that is, what should the player do? What should he use instead of D? You know the rationale behind the elimination of dominant strategy is the following, that if you eliminate a strategy, you will always have a better candidate there that you know you can always use instead of this one. So whenever you want to use this one, you can say, okay, this one does better. So why do I want to use this bad one? But the thing is here, which one should the player I use instead of D? It's A or B or C. The thing is we don't know which one is the truth. And there is no probability distribution for the player to evaluate the expectation of the gain for using each one of them. Therefore, we need to change it a little bit. This is our proposal for what this guy should do. We start almost the same. We look at the set-theoretic beliefs. Now, for each single one of them, we can do this two-step elimination. And we figure out that D is dominated by this strategy A. Now you do the same thing for each candidate, and you figure out that this not only D is dominated, but D actually is dominated by the same strategy A in each single case. And then we want the player to conclude that do not use D. You should eliminate it. And now you want to ask the same question, what should the player I use instead of D? And now I think at this point the answer is very clear. You should use A. Whether this is the truth or that is the truth, I don't care. A is better in each case.
But there might be something still even better than A.
That's true, and you will prove that if A is dominated by C in each case, then D is also dominated by C. Now, this is the idea behind the solution concept. That means, so we want D is eliminated, this cross means D should be eliminated. If it is two steps strictly dominated by the same strategy A for all type profiles in the candidate set, and the desired property should hold at all of the surviving profiles. This is how the name comes. So strictly just means that when we talk about dominance, we use strict dominance. So we do not want to give the player any ambiguity about whether these two might be the same or not. We want this one strictly better always.
Don't want to excite him, is the argument?
We don't want the players to depend on his beliefs about, for example, if he believes that the other players are not going to use some strategy, then this inequality may not be strict anywhere. So these two may become exactly the same. Then whether we should eliminate this one is unclear. And conservative just means that this same A, that this guy is really sure about something is better there. Now, implementation is usually what we mean, that after the players finish elimination, no matter what has left there, for all the surviving profiles, the property has to hold. So maybe we have 10 players, each player has 10 strategies left. Then at the end, we are considering 10 to the 10 strategy profiles surviving. But then we require the probability holds at each single one of them. And let me re-emphasize some points for this solution concept to show you that it is really not just some arbitrary one we take. So the first is that, as we just said, if we want to leverage this type of belief, we want the solution concept to be sensitive to these beliefs. And this is reflected by this for all quantifier there. So if a player's belief changes, then it is possible that the surviving strategies become totally different. Now, the second is that this is what the solution concept needs. It needs a player's rationality and mutual belief rationality. Meaning, as a player, I'm rational and I believe that you are rational too. So this is certainly a stronger requirement than just rationality. And you may want to think about why we do not rely on just rationality. The thing is, rationality will imply that you have to rely on dominant strategies. So I'm rational. I don't know what the other guys may do. Therefore, I can only focus on my dominant strategies. And as I have already showed you, dominant strategies will not get anything there. So to achieve this benchmark, we have to rely on something a little bit stronger than just rationality. And mutual belief is precisely what we need. And by the way, mutual belief is something much weaker than common belief. The common belief is that I believe, you believe, I believe, you believe, etc., up to infinity, that we are all rational. And I think this is a little bit too much to assume. Maybe for reality that we can imagine that in real life some players may hold mutual beliefs about each other. Maybe say I'm rational and I believe that you are all rational. But do I believe that you believe that I believe that you believe that I'm rational?
I actually don't see a big difference. I think that if you allow, once you allow the second round, it seems to me that they are more or less equivalent.
It's
a
not.
philosophical point. It's not a technical point, but
It may depend on observation. That is, I may have had some opportunity to observe you, but I don't know whether you've had any opportunity to observe me.
I understand.
So I believe you're rational based on what I've observed, but I don't have any beliefs about whether you think I'm rational.
If you will go 2 steps, so do you see similar reason to stop after 4 steps, say? That I believe that you believe
Depends
that
on
I
this.
believe.
There
No,
are
but I think
circumstances where 4 steps make sense and 5 steps doesn't.
Yeah, I agree completely, and I can imagine these scenarios, but in a general situation where you're going to apply this, so we may be very specific ocean you're going into where it will be the situation, but in general situations, you know, if you believe that other players are rational, then you believe you probably have a common knowledge about rationality.
Well, if something happened in public,
You might as well, because you couldn't observe anyway. It's a belief about the world, you know, your opponents, but maybe the more likely one is that they are irrational, you are irrational.
I think maybe you always, if you think about something happening in public, then it is easy that this public thing is common knowledge. But if something does not happen in public, then common belief may not be the case. That you see something I don't know, I don't believe.
It is, it's certainly theoretically weaker.
Yeah.
Well, I'm certainly happy if you believe that I believe that you believe that I'm rational. So the third thing I want to say that this conservative is there reflects the fact that we really want the player to hold a very conservative view about what they want to eliminate. So indeed, here the player wants to eliminate something if it is clearly bad. So it's really, according to this solution concept, maybe it is the case that the player cannot eliminate anything or eliminate very few. But then maybe you want to ask, because this is a so conservative solution concept, can we really implement something interesting at it? Because sometimes maybe the players cannot eliminate anything, so we cannot hope any interesting property hold there.
I believe that you won't put this slide if you...
That's true, otherwise I won't be here. I just want to give you the point that it's really a conservative thing there. Now, okay, so now this is why I'm here, as you said. So I'm going to show you this mechanism, how it's going to achieve this benchmark at this strictly conservative implementation solution concept. And actually, it is a very simple mechanism. It's normal form of the players act simultaneously only once. And this is what they do. So each player is going to beat a triple. The first is his ID. We put it there just for convenience. And the second is a bit, 0 or 1. And the third is a value, anything between 0, 1, up to the higher valuation upper bound. Now, allegedly, what do we want the player to put there? For the valuation part, we wanted to put there the guaranteed value. If you remember, the guaranteed value is that you take the max and you take the mean. And the bit, bi, we wanted it to be an indicator about this value compared to his own true valuation. So if it is equal, then it should be 1. Otherwise, it should be 0. Of course, whether the players are going to behave in this way is a totally different story. Now, how the mechanism is going to work? Mechanism is going to order the bits, so decreasingly, first according to vi, from the biggest to the smallest. If there are some ties happen there, then you are going to break ties according to bi. So you are always in favor to the player who declares that this value is about himself, with b is 1 there. And if there is still ties, then you break ties according to the player's ID. This part does not really matter. Now assume the order is something like that. So we call the first one player W, and we call the second one player J. Now the mechanism is always going to give the good to player W, but the price is going to be different. So if BW is 1, then he's going to pay the second highest value. Otherwise, he's going to pay the first, which is his own bid. Now, at this point, our mechanism wants to give the players more incentive to contribute their information. Therefore, we are going to reward the players some little stuff, which is defined in that way. Now, this is all the mechanism, very simple, as you can see. And how is this mechanism work? Well, I put this quotation around the analysis because at this point, I'm going to skip a lot of details. I'm going to lie a lot about this. Okay. But the basic idea is very simple. That is, point 1 you want to realize is that given this mechanism, by putting his own true valuation and the true indicator there, the true indicator there, always dominates anything underbidding. That is, put a number smaller than his own true valuation. Why? Because by putting his own true value there, if this guy gets the good, he's never going to pay more than this much. So this part, he's not going to get any negative utility. But the last reward is increasing according to VI, as you can verify. Therefore, he gets more reward in that part. So no matter what he wants to do, he doesn't want to underbid in this way. But once we establish this lemma, this the next thing we want to say is about what happened in the second step reasoning. That is, given a player's own belief BI, by telling the true guaranteed value and the true indicator is always better than anything underbidding in that way. Putting any number which is smaller than his guaranteed value is not a good idea. According to his BI, of course. Because according to BI, the true valuation has to be one of these profiles in BI. And there will always be some player whose valuation is at least this GI. And this guy, by lemma 1, is going to put at least this much value there. Therefore, this player, he may win or he may not win, but whether or not, he's not going to pay anything more than his own value. And then, again, he gets more reward in the last part. This is how the reward is defined, to encourage the player to tell the truth. No. This says that given BI, that is, a player is only going to reason according to BI. So he's going to compute his utility, assuming that the true types is in BI. And of course, if we establish the fact that the players are not going to underbid, then you will going to realize, okay, each VI is greater than GI, and then the second highest of VI is at least the benchmark. Then the player W, no matter what his price is, it is at least the second highest. Therefore, we are going to get the second highest the benchmark there.
For lemma 2, was that strict or was just?
The better there, it is strict. So we use strict dominance. Actually,
So there is some chance, but if the player thinks that there's no chance, I mean, in that example that Encore gave, what do you mean? Let's say your values are 0 and
you believe the other guy is very high, and you don't think you are going to win the good. And then this part take care of that, that you announce a bigger value, you get a more reward. And the only risk you need to take is, the risky thing you may think is that you may end up winning the good and pay the high price, right? But this part and the lemma 1 tells you that you believe the other player's valuation is that high, therefore you believe that the other guy is not going to underbid lower than that. Therefore he's going to win, and you are going to declare his price. All right, this is all we need to say about how the mechanism works. But there are something I want to point it out, which is not in the analysis. That is,
So just to make sure,
yeah.
you got the second, but minus a little bit because of...
Yeah, exactly. We might lose this little bit of epsilon reward.
You know that you cannot get exactly the second...
If you want to use strict dominance, we don't have impossibility result about this epsilon, but we believe this is not easy to get there. Because if you want to give them strict incentive, you have to give something. So
there's a literature on robustness of mechanisms which says, suppose that that my beliefs are not held with 100% certainty. That there's at least a small chance that my beliefs might be wrong. Is the outcome going to survive that kind of uncertainty? It appears that this kind of mechanism in general is not going to survive that kind of uncertainty. Again, going back to the same kind of example, if there's at least a small chance that the other person doesn't have this very high valuation,
yeah, but then, yeah, I think what the model is something like, if you take this belief, then you take the case that this belief is a belief. And if you are not sure about it, then what you can do is you always enlarge the belief set until you reach some point that you are comfortable with this belief set. And at that point, that will be the thing we are trying to leverage. And this will be the benchmark defined on that part. Okay, so one thing I want to point out is that this mechanism, actually, regarding your question, why this is kind of what you said, that give the player some small reward, right? But the thing is, this type of mechanism, it can rule out underbidding, but it cannot rule out overbidding. That if a player want to announce some higher number to get some reward, he might want to do that. And therefore, tell the truth is not dominant. It's not. You cannot rule out that. And another thing is about participation. That why a player want to participate in this type of thing. That is, as you can see, if the beliefs are correct, then you can guarantee that the player will always have non-negative positive utility. And then, because a player is going to behave according to own belief, right? He's not going to think my belief is wrong. Then he's going to enlarge the beliefs until he thinks it's correct. And then this player always have incentive to participate. And let me give you some very quick summarization about this mechanism. So how about the following? We say that the second belief mechanism implements this benchmark when the players have external information. Now, I want to say that this is actually not the correct statement. And the statement is the following, with the last line removed. The mechanism implements this benchmark period. And why we want to emphasize this, because this is really the reality that the set-theoretic belief always exists. It is not an assumption. You can always write down the set of candidates and work from there. And therefore, from our point of view, really, we are not looking at just this theta. We are looking at the player theta together with the beliefs. Okay, there are some things that we have been asked before, so maybe I can clarify a little bit. So people will think, what if, so when trying to look at our mechanism, some questions look like, what if the players are irrational? What if the players do not have quasi-linear utilities? Or what if the players do not care about the absolute reward? And then how is our mechanism compare with the second price mechanism, for example, which get exactly the second highest valuation without this minus epsilon, right? The thing is, point one, we feel this epsilon reward is necessary there. And of course, we can scale it up to give the players more reward. But given that we want to work in revenue, if we want to get a high revenue, you cannot expect to give the players much. So epsilon is there to provide them the correct incentive. And then for the second price mechanism, if you want to ensure the player's participation, even when a player doesn't believe that he is going to be the winner as what we have talked about, then why he wants to show up in the second prize is not clear. And then if you want to give the second prize mechanism some incentive for the player to always participate, you need to impose some epsilon reward there as well. And therefore, from our point of view, really, if you want to put these two mechanisms in a fair ground, then you are going to figure out that no matter what happened, a second belief mechanism is always at least as good as the second price. And to summarization a little bit, what we have today is that I think I have showed you that the incomplete information case can be modeled in a less demanding way, less demanding than a Bayesian, and yet still workable. And there's no classical solution concept capable of implementing this benchmark, which is always more demanding. And then for this class, for our solution concept, which is very conservative one, we actually provide some new power and enable our mechanism to get this benchmark. Maybe this picture is what you can take after the talk. So if you want to stick to some classical method, classical model, then basically you cannot leverage this type of information. But as Archimedes taught us that if you cannot leverage something, maybe you have the wrong position of the fulcrum. And if you have a fulcrum somewhere, then you can leverage anything. And this is what we do, and we believe there are a lot of things to be done in this direction. So that's it. Thank you.
Okay, thanks again.
Thank you. Thanks.